I'm a data scientist for the past 2 years at Elsevier, and I served Elsevier for the past 8 years, actually. Today I will focus on recommender story, but how we try to transition our backend from Map Reduce to Spark and improve quality, reduction in cost. But first, I'd like a show of hand. How many of you have ever heard of Elsevier? Okay, quite a lot. So Elsevier is a global analytics company. It's delivering solutions for science and health. We've been there for the past 140 years, and you mostly know us probably as an academic publisher. We're kind of the biggest one, but we have always managed to combine data, high-quality data from our journals, but others as well, with technology since a very long time. And we do that to empower our users. Basically, we try to serve researchers, engineers, and health professionals do what they do best, which is research, develop, and treat people. And today I'd like to talk to you about Mendeley. Mendeley is one of our solutions that helps academics stay on top. And it does that by by providing reference management solution, academic social networking, managing data sets, finding job opportunity as well as funding opportunity, and we do that again, merging data with search and discovery tool. Such a discovery tool is MendeleySuggest, one of our oldest recommender. It recommends articles. And recently at Rexis, one of my colleagues presented how it impacts researchers and how many documents they're adding in their library through Suggest instead of through other means. This is particularly relevant for users that are not very intense in using Mendeley in general. Basically, MendeleySuggest use collaborative filtering. So very simple. You combine the data from multiple users that best resembles you. And then you serve everything those users have in their library, because Mendeley provides reference management, and we remove what you have in your library. So we need for this quite a bit of data. We need our user profile, a few millions. We need the content data. And yeah, it's just a whole mashup. Today I'd like to focus on the article bit and the user profile, because the trick is it's user-generated data for the vast majority of it. So the question, when a user enters, for example, a title matrix, is it the same as in the other user library, the matrix? So you need to deduplicate to make entities of a document and therefore serve the document. Those entities, we call them canonical documents. They are a cluster of whatever their representation is in user's library. The problem is, over the years, we have had issues reported by user. Typically, I've already have this document in my library, or why do you serve me two documents exactly the same? Here, for example, just the author order is shifted, and the original deduplication algorithm didn't figure that out. Another thing is we have another interface which is done through search, and having those records, canonical records, being split among multiple entities, also split, for example, the ranking and the popularity ranking of those documents. So being able to aggregate them correctly is a paramount to be able to serve good recommendations and provide relevant search. So the original algorithm was designed somewhere in the 2010s when Hadoop Map Reduce was basically the top of the game. And if you want to figure out more about how it was done, you have this article. And today I want to focus mainly on the gray box at the top. Can I show? No, I don't know if people can see. No, yes, here. And I don't know if you can see over there. Difficult. I will stop. And the box that is circled in orange. One of the difficulty is when this original algorithm was designed, basically Mendeley had about 100 millions of records. And over the years, we grew and grew and grew. Now we are at about 2.2 billions. And, well, the system doesn't work well enough anymore. So we had a blank slate, and we had to redesign everything without breaking, obviously, because there's a service attached to it, and users like it. So we need to improve the overall user experience by improving the classifier. We need to improve the scalability by improving processing speed. And we also had another requirement, which is our developers didn't want to maintain old Hadoop Map Reduce code with Java. They prefer to move to Spark and Scala. So Spark and Scala, it was Scala because we like type safety. But the first problem is classification. So these are examples of data you may be able to find in our database. We mainly process the metadata of those documents. So things that may look the same are actually different, and things that may look different are actually the same. You may have issues with documents that are in other language than, for example, English. So they will be indexed in English, input in the system in English, but another user knows that actually that's a French document and put the French title in it, which is sometimes problematic. So we had to improve the classifier. Obviously, we didn't start from nothing. So we re-engineered a few features, train, test, model, with the previous datasets that we had. And what we had to do also was to generate new pairs at the decision boundary for the models, because we thought the old classifier was good enough, but it turns out it's not so good. So once we had those pairs, we had to manually annotate them. So we use mechanical Turk, and here comes another problem when you have non-specialized user annotating your data. Well, sometimes you kind of get garbage, and you spend a lot of money for not too much. So we did with what we had. So out of 100,000 pairs that got annotated in triplicate, we recovered about 27,000. But once we have this brand new model, you need to benchmark it. Is it performing better than the previous one? And also, which matters when you do big data, is how fast does it. If it's not fast enough, maybe you need to re-engineer some of the feature so that it does better. And lastly, you need to deploy into your production environment. So we need to deploy into Scala in our case. But when we started off, our data scientists were working in Python. So that created a lot of issues because our data scientists loved SVM with RBF kernel, which was very difficult to port in Spark. So we had to work around and try again. And in the end, we had a random forest. The second part is the scalability issue. So before feeding your data to your classifier, where you can do dumb pairwise comparison, the problem is with 2 billion items, that doesn't scale well. It will take years to process if you have the money to use all the machines. So you need to kind of reduce the cardinality. The first step to do is get rid of the junk. There's no point putting through the classifier things that will never be shown at the end of the process because of business rules. Second part, we applied some exact duplicate detections and also an identifier base, because if you can solve everything with a simple group by, well, why wouldn't you do that? And then there's the hard cases, which means we use a tunable blocking step with min hash LSH. And the last trick is obviously because our problem is not directional. Well, if you solve the pair AB, is it a duplicate? You don't need to solve the pair BA is a duplicate. So you can divide your task by 2 after your cross join. But another thing that also matters is data normalization. Our data is kind of dirty. Make sure that you have everything lowercase, remove punctuation, remove double spaces, all those kind of things, and more, like XML, LaTeX, and whatnot. And so how do we perform? Well, here are the results. You can see the old model with the old deduplication algorithm. Its F-score was quite honorable with 98. But if you look at it with the new dataset, it barely performed above random. So now we have not only kept the old performance on the old dataset, but now we have a much better performance with the new dataset as well. And the compute time has reduced from 24 hours to about 13 hours. So that even if you're using a spot instance in Amazon, that's still a ton of money saved. And for our users, our records that was split over several hundred items now are mainly about 2. We still have difficulties, but thanks to the popularity ranking in the search, well, this one that is at the bottom is way, way, way far. So that's not so troublesome. Another thing that I want to highlight is when you play big data, well, you may think 3% error is acceptable, except that 3% error over 2 billion, that's noticeable for our users. So you need to balance how much you want to spend into improving versus the feeling of your users. So the lesson that we learn is you need to monitor your systems, not just whether the server are alive, but also the quality that they output. Your data does matter. So you need to know your data that allows you to take shortcuts. And very importantly, more data doesn't matter so much. What matters is good data. For engineering, keep it as simple as possible and make sure you have extensive testing. As I said, our proof of concept was developed in Python. We tried to migrate an SVM with RBF kernel into Scala. That didn't work easily, so we thought, let's treat the inference part as a black box. We will develop the features in Scala, except that without tests, we had problems with features that were out of order in the vector. We had problems with libraries that compute similarities that don't perform the same way into different languages. So yeah, that's quite important. And another tip that we learn when we do the exact duplicate step is you may think using a hash is very useful because that reduces shuffling and so on. But beware of your hash because sometimes they just collide. As we didn't apply more advanced classifier afterwards, well, we had really garbage data coming in because of hash collision in our data. So yeah, as a data scientist, which I am, I'm not a software engineer, make sure you collaborate very well with the engineering teams that will be putting the production-grade code. They are the ones that will maintain it over the years. They are the ones that do the optimizations, all the operational optimization. If they cannot touch your code, then that's not helpful. And you may not want to be attached to this problem forever. And with this, I'd like to thank you. And if you like solving problems, well, come join us and come visit our booth in the exhibition hall. Thank you.
Great, thanks, Jacques. We'll do about 5 minutes of questions. Does anybody have questions for Jacques? I'll go around and pass the microphone. No questions? All right, thanks again.
Yep.